The topic of discussion is the equivalent of mass and energy. We know that work energy from the work energy theorem that kinetic energy of a moving body is equal to the work done by the external force that imparts the velocity to the body from rest. So if F is the force acting on that body, then work done by the force on body in raising its velocity from 0 to v is defined by this formula, where W is work done, F is that force acted on that particle externally, and ds is the displacement. So F dot ds is the work done. But how much work is done in totality when this particle acquire the speed from 0 to v? That will be the total kinetic energy of that particle in motion. So we can define kinetic energy in this way. Kinetic energy is equal to this work done is equal to limit of integration 0 to v f dot ds. In the next line, what we are doing, we are just multiplying and dividing this factor by dt. So this ds upon dt becomes velocity, and we can write limit of integration 0 to v f dot v dt. Again, we know that force is the rate of momentum, so where p is equal to mv. So we can write the complete formula in this way: 0 to v dot d upon dt mv dt. We have just interchanged these two terms because we know the property of a scalar product: a dot v is equal to b dot a. So we are writing first of all this v, and then after this d mv upon dt. So in a simple way, we can define this kinetic energy: limit of integration from 0 to v dot this differentiation of mv. So this is our first equation, and from this equation we have to derive the relation for the kinetic energy. We know that this formula from the mass variation relationship: m is equal to m naught upon square root 1 minus v square upon c square, where m naught is the rest mass, actual mass, proper mass of the object, and m is the mass appear to the s observer. Where why we are saying here s observer? Because the origin of this formula is related to the inertial frames. So EK, kinetic energy, is equal to 0 to v dot this differentiation of mv. Now we are putting the value of m from this relation, that is m naught upon square root 1 minus v square upon c square, into this v, that is this one. So basically what we have to do, we have to just solve this part by parts method, because it is also a function of v. M is also a function of v. So m naught is a constant quantity right now for this formula. So kinetic energy will be equal to m naught comes out from this relation. So you are getting this limits of integration 0 to v, then this v, this is, and differentiation of these two terms 1 upon v, and this is 1 upon square root 1 minus v square upon c square. So you can write in this way also: v 1 minus v square upon c square raised power minus 1 by 2. So further, kinetic energy is equal to m naught, this m naught 0 to v integration limit v this term and differentiation of these two basically is this result. First part 1 minus v square upon c square raised power minus 1 by 2 this term, and differentiation of this term dv minus this factor minus 1 by 2 into this one, that term, and differentiation of this one 1 minus v square upon c square raised power minus 3 by 2 minus n minus 1, differentiation of any object d upon dx into xn is equal to nxn minus 1. So minus 1 by 2 minus 1 after differentiation, that becomes minus 3 by 2. So this is that one, and again the differentiation of this part will be minus 2v upon c square into dv. So after simplification you can write this in this way, and this becomes m naught, kinetic energy becomes m naught 0 to v integration limit this v, and now take out the common of this factor 1 minus v square upon c square raised power minus 3 by 2. So you are getting 1 from 1 minus v square upon c square plus v square upon c square. From here you are getting this factor 1 minus v square upon c square, and from this result we are getting v square upon c square. So this term cancel out, and we are getting kinetic energy is equal to m naught integration limit 0 to v dv. The remaining factor is v dv upon square is 1 minus v square upon c square raised by 3 by 2. Now to solve that equation we are just substituting the value of 1 minus v square upon c square in this equation, in the last equation. Instead of this we are putting the value of this y. So after simplification we are getting dy is equal to this factor minus 2 v dv upon c square. So after substituting these values we got this result, ek is equal to minus m naught c square upon 2 y minus 1 by 2 upon minus 1 by 2 raised by 1 minus v square upon c square. So further simplification of this mathematical part is this one, and after opening this bracket we are getting m naught c square upon square root 1 minus v square upon c square minus not c squared. So ultimately we are getting this result, kinetic energy is equal to mc square minus m naught c square, where mc square is the total energy, m naught c square is the rest mass energy of the particle. So this was the explanation of the relativistic kinetic energy.